Okay, thanks. Let me see. Okay, so this talk is really divided into two parts. The first is going to be talking about the experiments, as Richard said, and it'll be critical of the experiments, and they shouldn't take this personally, because the second part will discuss theory, and it will be critical of the theory, and a lot of the theory was done by myself. So it's actually going to be trying to say that maybe something's wrong with that theory. Okay, so before I start, I just want to acknowledge Jorge Hirsch, with whom all this work on the hydrides was done. He was the driving force, and it's been a really good collaboration. Here's a very brief outline. I'll just give you a brief introduction that maybe isn't needed here. Then I'll discuss, as I said, the hydride experiments. And then if these materials are superconducting, then I want to address the question of the electron-phonon interaction. Because, you know, for those that are younger, you may not appreciate that Marvin Cohen and Phil Anderson wrote a very influential paper in 1972, where they basically did a back of the envelope type of calculation and said the maximum TC that could be achieved from electron-phonon interaction is about 30 degrees Kelvin. And that was invoked many, many times over the years, especially when the cuprates came along. And then when magnesium diboride came, they said, okay, maybe it's 40 instead of 30K, no problem. But since the hydrides have appeared, there's been complete silence on that. So there's those issues that were raised, which were valid issues, have not been discussed further. So I'm not going to discuss them directly. I'm going to discuss another aspect of the electron-phonon interaction, but let me begin. So all of you know superconductivity started with Camerling-Owens, and you know that it involves zero resistance, and then this is a resistance plot versus temperature for mercury, but it also involves the Meissner-Aschenfeld effect, okay? And that's where a magnetic field is expelled from the superconductor. And these are two different things. The first set of figures represents flux exclusion, and this will be important later on, as opposed to, which is something that follows from Faraday's laws. And then the second set is flux expulsion, and that is what is key to superconductivity. So when you see this picture that you're all familiar with of a levitating magnet, this is not the Meissner effect, right? For me to show you the Meissner effect, I have to show you a movie. I have to show you this thing actually popping up. Okay, the timelines you've seen quite a bit of, but just to tell you where I'm coming from, you know, this is a bit out of date. So if I include further developments, then what you may have noticed I slipped in here were question marks beside this, you know, theory is well understood. Because when I see this many families of superconductors, and many of these families have are believed to have different mechanisms driving the superconductivity, I get uncomfortable. So, and that's a bias, that maybe that's the way nature works. But my bias, just to let you know where I'm coming from, is I feel like there should be some more unity. And so so when the hydrides appear, all of a sudden, that includes those. And so that's what I'm going to discuss next. So just how I got involved in this was relatively recently with the 2020 announcement of room temperature superconductivity that we'll hear about presumably later on, and we've all already heard about it. And when we first saw these resistance curves, they looked really sharp. That's what was first striking, because these are for sure going to be inhomogeneous samples, just the way they they do the heating to get these to go superconducting. And to have sharp transitions like this seem very unusual. Here they are again on the right with different applied fields. And what was striking was that they remain sharp. There's susceptibility data over here. That's another issue that has been addressed, and I won't touch on that here. So I just want to let you know that this is how we kind of got drawn into the world of the hydrides. These struck us as unusual, and so we investigated this further and eventually wrote a comment, or it's called Matters Arising in Nature. So when you compare it to other known superconductors for reasons that are reasonably well understood, the transition tends to broaden out, especially when you apply a magnetic field. This is a yttrium example, and there's a magnesium diboride and many other examples of superconductors where this is true. So that prompted us, as I said, to basically write a short comment pointing this out and wondering why this was the case. Here's a plot of the actual transition width versus applied field in normalized units. And you can see it's very striking how CSH remains flat compared to the others. And we weren't alone in this. Cohen and Dogan submitted a paper as well a bit later, as did, this is just a general review, but they point out that there's some issues here as well. So I'm not going to dwell on this part. There's just a brief summary of some of the figures involved, and you can read those papers to learn more about that. But once drawn into this field, we then looked at older work. So beginning with this famous paper from Aramitz and co-workers, which was back in 2015. So if you look at their first figure, I mean, if you look down here, the magnetization plots are very striking. There's this huge background, and that's understandable because of the diamond anvil apparatus and the gasket and so on. And if you look at so if I blow up that one figure there and look at the extracted magnetization, then I mean the good part is the in the zero field cooled case, the magnetization does follow the resistivity, which is in red there. So that's great. But for the field cooled, which is really what you need to look at for the Meissner effect, there's absolutely no sign of anything happening at the transition. Okay, so there's no Meissner effect here. And that's not totally unique to this sample. That sometimes happens because of flux trapping. So you try to the field tries to get expelled, but it's trapped inside the sample because of pinning centers and so on. So in any event, the Aramitz group attempted to improve these measurements, I think partly as a response to some of our concerns. And so they came up with slightly better data several years later. But once again, the red is the field cooled, and there's no sign of anything happening there. So even with the improved samples, and again, this is not in itself damning, but you know, I don't. They have Meissner effect in the title, and then that's what. Actually, it's not in the published title. I guess the referee told them to change that, and it wasn't us. So it has yet to be demonstrated. And this paper also, this was a good paper because it showed exactly what they did. And when you look in their supplementary material, there is this, to me, very disturbing set of curves. So this is the superconducting sample, basically what I just showed you. And this is the non-superconducting sample. There's no superconductivity here. And in both, of course, the field cooled stuff shows nothing, but the zero field cooled, which showed something in the superconducting sample, actually shows something in the non-superconducting sample at, coincidentally, basically the same temperature. And we've asked them about this, and we haven't really got a good response. I mean, they don't seem as concerned about this. They think there's probably something in there that's caused this, but this is too much of a coincidence to be just left hanging, I think. So this is a very bothersome point. Let me see here. So anyways, that paper eventually got published, I think, in this form just a month or two ago. Okay, so I'm not going to, and we did quite a bit of analysis of a series of papers, and I'll refer you to this. So this is a kind of a review that I think is posted on the archive or somewhere else now by Hirsch himself. And it's got this nice summary plot here, which shows you that these new materials really don't fit the mold with known superconductors, which doesn't mean anything. I mean, they don't fit the mold if their TCs are above 200 degrees, but it's just that if you look deeper into these papers, you realize many of the parameters that are a consequence of the measurements concerning these two superconductors are quite unusual. So for example, the critical currents densities that are allowed are several orders of magnitude higher than anything we've used in the similar anomalies with the HC1s. And there's some inconsistencies with measurements of HC1 depending on the method used. I'll leave it at that because I don't want to really get into that. So I did mention though that it is sometimes the case that in field cooled situations, you basically get very little, usually not zero, but in this case, it looks like zero expulsion. And that could be due to flux trapping. So we wrote this paper pointing this out. And that one could simply do exactly what Bednorz and Mueller did. So if you look at there's an original Bednorz and Mueller paper, and then I think there's a quick follow-up. And then they went after the persistent currents because they had the same problem. They had very little field expelled in their sample. And so they looked for basically persistent currents. So you field cool the sample, then you remove the field. If you remove the field and it has remained in the sample because it's trapped, then it remains trapped. And in order for this situation to be viable, you have to have persistent currents. So that will last for hours, if not days, if not weeks. Okay, and that's a straightforward experiment that can be done to investigate this. So that's what the Aramitz group then went to do. So that's in this preprint from, I can't read it now, but I think it's June of this year. This is Minkoff et al. Now, so here's the results that they got, and these are all magnetic, trapped magnetic moment that has remained after the field has been removed. Now, the trouble is, I'm not sure why, but these are all zero field cooled, except for the 4 Tesla result. So the 4 Tesla result is buried in this group of results here, and I guess it looked the same to them, so they thought, well, it doesn't matter whether you zero field cooled or field cool, but it does matter. So they did an analysis of their experiments, and these curves, which, here's a blow up down here for the trapped magnetic moment, these fit really well, their data. And they're based on what's called the beam model. So I'll come to that in a second. But the trouble is this, as far as we can tell, this is the right analysis, but for the wrong experiment. This is the analysis for the field-cooled experiments. And they actually did zero field-cooled, except for that one red point up there, which is field-cooled, but there it's in the saturated region. So as you'll see in a minute, that doesn't matter. So we immediately wrote this paper that does what we think is the right analysis. So this is all based on the beam model from 1962, really. This is a review article from 1964. And, you can either field cooled, in which case the magnetic field is throughout the sample in the normal state, then you go below TC and it gets expelled. But if there's flux trapping, the beam model says that the profile will look like this. And basically the slopes of these curves, which are constant everywhere here, are determined by the critical current density. So that's the premise of the beam model. Okay, and that's what they used, and that's what we use. But there's a different configuration. I won't get into the details, whether it's field cooled or zero field cooled. So if you do the zero field cooled analysis based on that same beam model, you get this red curve, not the black curve that they have. That's what you get from field cooled. Well, we get it. This is our result, but it's done. We had to modify H star. They had a typo or a mistake of factor of 2 in their results, which was inconsequential because H star is really a fitting parameter. But you can see that it's a very different curve. And if you try to fit the zero field cooled, which we did here, you can try and fit it to the low field data. If you look at it closely, it doesn't quite agree, but it's not that bad. But you will not fit the high field data if you try this. So that's where this stands right now, because it's only a few weeks old, and so I would say that the evidence for trapped flux, which would really decide this, I think, is work in progress. Okay, Richard, what's the timing like? 20. So maybe I'm gonna I'm gonna skip the optical measurement. So this is another paper done in collaboration with Tom Timmis' group that purported to see the transition in the optical experiments and also find evidence for a boson exchange, which we don't, Tom graciously shared the raw data with us, and we just don't think that it's there. But I'm not going to go through that story for sake of time. Instead, I want to turn to the second part of the talk, which is suppose these are superconducting. Density functional theory tells us that the superconductivity is driven by the electron-phonon interaction. They're calculating TCs that are in close agreement with the experiment in some cases. And so nonetheless, in spite of that, I want to address one particular issue about Migdal-Eli-Ashberg theory, which has bugged me from the first days I started using this theory. And it's what I call the Achilles heel. It's the Coulomb interaction. Okay, and I'm going to address one small part of it because there are many aspects to this problem. So first of all, what is Migdal-Eli-Ashberg theory? Let's back up and look at BCS theory ever so briefly. So most of you are aware this was 1957, this discovery, and there's the wave function. And you can look at various features of it that I'm not going to get into, except you'll notice it's it's all in wave vector space. So BCS theory is entirely in wave vector space. Okay, and that's going to be important. When we go to Ellie-Ashberg theory, I'm not going to get into the nitty-gritty, but it includes the dynamical electron-phonon interaction. So just like we all learn about the Coulomb potential, and then later on, if we want to investigate it a little more closely, we actually describe it in terms of virtual photon exchange. And so there's this retardation effect given by the speed of light, which we normally ignore for purposes certainly in condensed matter, but even in everyday occurrences. So here, there is an exchange of a phonon, and the phonon is something on the speed of sound. And so that's a much slower time scale than the Coulomb interaction, which, as I said, is the speed of light time scale. Okay, so it builds on the Migdal theory of the normal state, and this graph is important, I think. So first of all, this graph is plotted versus frequency. Okay, and so all of a sudden there's this frequency axis that doesn't even appear in BCS theory. Okay, there is all the K-dependent phenomena that occurs in BCS theory, but it's not important in Ellie-Ashberg theory. It goes into the density of states. It comes in if there's anisotropy in a particular system, but I'm going to talk about the isotropic case here. You'll also notice that I draw this, again, most of you who have learned about superconductivity learned that it comes from an attractive interaction, and you wave your hands about two electrons attracting one another. In fact, you've probably been told wrong. The interaction is repulsive everywhere as a function of frequency. It's given by this graph, or that's typical, and it's a cartoon version. The key is that in the case of an electron-phonon mediated exchange, the interaction is slightly less repulsive at low frequencies compared to high frequencies. That is the key. And when that happens, basically you can fold this problem from the high energy scale down to a lower energy scale. And that's what Tomolkov and Morel and Anderson did. And then the effective interaction looks like this. And now it looks like there's an attraction at the Fermi level and over a width omega Debye, and then repulsion elsewhere. And you'll also notice the very important feature that repulsion is much smaller than what it was up there. Okay, and that's all. To be honest, from my point of view, this is a numerical trick to make the numerics much faster. That's all it is. Like I can converge these equations with the cutoff out where it's supposed to be and get the same answers. Okay, and so it's just a numerical trick, but it has physics content, and the physics content is the retardation. So here are two electrons. The first electron, and this again is a cartoon, although I've made it better than most because I've tried to conserve momentum. But this electron polarizes the lattice in its vicinity and then gets scattered off. And the second electron from below, which is drawn in pink, which is horrible because they're indistinguishable particles, but let's not worry about that, is attracted to where the first electron used to be. So it's a retardation effect. And because it's attracted to where the first electron used to be, the Coulomb interaction isn't going to be as strong because the Coulomb interaction is roughly instantaneous. So that'll occur when these two are nearby to one another at the same time. So this is actually the physics that's encompassed by that renormalization of mu star. Ellie-Ashberg theory was developed by Ellie-Ashberg when he wasn't just a graduate student, he was a starting graduate student, if you can believe it. And there are these input parameters. So BCS theory requires some effective attractive interaction and omega Debye. Here we need alpha squared f, which I'm not going to focus very much on. And then we need this Coulomb pseudopotential. Okay, and this Coulomb pseudopotential has been quoted many, many times in this conference and in the literature over the last 6 years, and it's a bit irritating. I've done it here as well. You know, this is meaningless unless there's an argument here which tells me about that energy scale. Because like I said, I get the same answer even if I don't do this normalization. So for this to make sense, I have to tie it to that. Now, the reason why it's left out in a lot of the literature is because people go on and use the Allen-Dines equation, and then there they don't care. But if you're doing hydrides, you know, the phonon energy scale is an order of magnitude at least higher than what we're used to. So that differential of EF to omega Debye is not what we usually think it is. So we shouldn't be too surprised if mu star comes out large, basically. Okay, so and that mu, you know, that's like the Hubbard U. That's a big number, and there's not, you know, there's some kind of screening and stuff, but there's not a lot of arguing that you can do to prevent that from being a big number. That's a big number. The reason why it might be rendered relatively harmless in superconductivity is because it gets reduced to mu star in the fashion I just indicated here. So then we talk about this effective Coulomb repulsion, which is mu star. And the question I want to ask, so this now enters as a competition to the pairing. Okay, so already we've left out the fact that all the quasi-particles in the problem get renormalized because of the Coulomb repulsion. So there's lots of things that happen in the single particle self-energy level that are not even included in this. So I'm not including that part at all. But I am including now, I want to include the fact that mu gets reduced to mu star, so that enters into this lambda minus mu star effective potential. This is, I don't know if you've seen this cartoon. It's one that Phil Anderson published because he was trying to make fun of the spin fluctuation theories, which he considered to be the mouse. And then there was the J and the U in the problem, which were, you know, the elephant in the room, so to speak. And this is what I would apply to electron phonon problem. We've always, me for starters, in more recent years, have focused on the mouse, which is the electron phonon interaction, because it gave us all this beautiful structure and did all this kind of neat things. But the big energy in the problem has been the Coulomb, the direct Coulomb interaction. And we're not really addressing that in the hydrides very much, as far as I can tell. Okay, so here again is that effective interaction. And so the question is, how well do we trust this? So let's see. So to tackle that, I'm going to use what's referred to as a toy model. So this is the Holstein-Hubbard model. So this electron phonon interaction just involves Einstein oscillators. They're independent, so that makes it easy. This is the displacement. So it's just coupling the displacement to the charge. And then we're putting in an on-site Coulomb repulsion. So this is the minimum model. I'm going to actually present results for a simple two-site model, but based on other calculations, I believe this is applicable to the infinite site system as well. And again, what I'm going to do is simply calculate the binding energy between two electrons and find out if binding exists, which in the way I'm doing it, the delta that I calculate will be above 0. If binding does not exist, I'll get a delta less than 0. Okay. So what are the expectations? Well, based on what I told you for that mu and mu star business, if we translate that into this Holstein-Hubbard model, then the mu is just the Hubbard U, and I get this renormalized Coulomb interaction like this. So if I look at the dimensionless quantity, which is this mu star, it's given by this expression, or supposedly. And so with this expression, you see that even if U is infinite, then this mu star reduces down to this number. Okay, it's and so that can be a reasonably small number if the bandwidth W is much greater than omega E. So I just put some numbers here, you know, that's close to the canonical 0.1, but then it can grow depending on what that ratio is. And you can also argue about how valid that is, but that's just to give the context. This is what we expect, right? So if you have a lambda value greater than 0.145 in this case, or greater than 0.4, you're going to get binding. Okay, even when U is infinite. This is because of the retardation effect. If you believe this expression. So, like I said, there's been a lot of work on this in larger systems, and I particularly point to the work by Barisic et al. Banca et al. With Stuart Trugman that can do the infinite system. I'm just going to show you two site results for simplicity. There's another thing that comes in here, which I just want to mention briefly, which is the polaron effect, which is just a single particle problem. And this is ignored by Migdal-Eli-Ashberg theory entirely. And so it's ignored by density functional theory, or at least by the part that gets attached onto density functional theory to calculate superconducting problems. So if the material goes polaronic, we wouldn't necessarily know about it. So these are just older calculations for the infinite systems in 1, 2, and 3 dimensions. And what you see here, I plotted the effective mass versus lambda. So this is the same lambda that shows up in superconductivity, and you see that the effective mass goes through the roof depending on dimensionality, etc. But it goes through the roof for lambda less than 1. So we've got to worry about this when we're thinking about these model calculations. And there's more nuanced arguments about why this might be okay, because lambda itself grows as interaction grows. So these are bare interactions. Okay, let's just go to the calculations, which are given here. So this is a bit of a busy graph. Here's the binding energy. So that's these curves versus U. Okay, and this is for lambda 0.5. It's just an example system. And I've calculated for various ratios of this phonon frequency over the kinetic energy parameter T. Okay. And I've also plotted, which in this case for lambda 0.5 is largely irrelevant. I've plotted this is the number of phonons in the ground state, which is kind of a proxy for the effective mass, because with 2 sites, I can't really calculate an effective mass. And these are small numbers, so that's kind of okay. But what you see, and for the interaction to be repulsive to begin with, the U here has to be greater than 2. So basically there is this small region in which you get binding. Okay. In fact, so when U over 2T is greater than 2.3 or whatever it is here, you no longer have binding. So remember, the Morel-Anderson result said I could take U go to infinity and retardation would save me. But this is saying quite dramatically, but no, you can't tolerate very much of a U before this stops happening. Same calculation for lambda equals 1, which I don't really want to believe because now polaronic effects are very strong. Has the same issue in that it goes to 0 at some finite value, so it doesn't go to infinity. Binding ceases for rather small value of U in comparison to what Morel and Anderson would tell us. Okay, so that's and there's all sorts of caveats here, and I've only used 2 sites and so on, but there have been calculations like this for the infinite system as well. And they're all consistent with this, because with a local model like the Holstein-Hubbard model, you don't have to use very many sites to capture the phenomena. Okay, I've got to stop. So here's the summary. So as far as the experiment is concerned, we've been told time and again, and that's absolutely true. The experiments are very difficult, but that doesn't mean we shouldn't do them. I think we need that the stakes are so high here that we need to have confirmation that these are superconductors through the Meissner effect. And if you can't do the Meissner effect, the flux trapped experiment with persistent currents is just as good. We discussed this a bit this morning. We need the reproducibility. And then this issue I raised this morning as well about the theory being based on density functional theory that doesn't have all the controls in it, just like the Migdal-Ashberg theory doesn't have all the controls in it as well, right? So I mean, I might be corrected if I'm wrong, but if your system goes polaronic, I'm not sure the density functional theory will pick that up. And then the emphasis on retardation, that clearly does play a role, because in fact we do get binding even though U is larger than what the attraction from lambda would be. It's not nearly as effective as when what you would expect from the Morel-Anderson expression. Okay.